All right. Happy Wednesday. Almost getting to the end of class here, but today we'll be continuing talking about metamorphic rocks, and it is Earth Day, so happy Earth Day. Hope you guys can go outside today and enjoy what's around you. It snowed in Burlington this morning, so that's great for the end of April. But anyway, let's talk about just logistics again, just as a reminder what to do this week. The lecture quizzes on Blackboard for days 37, 38, 39, Monday, Wednesday, Friday. Lab 10, I sent out an email and posted the assignment on Blackboard. And just a reminder that this is a creative assignment, and if you are having trouble kind of thinking of an idea, just email me, message me on Teams, and I can help you think of how to mold your idea. I don't want to hold you guys back on whatever topics or way that you want to present. So creativity is encouraged. All right. And then the chapter 8 reading quiz. All right. And then just the optional assignment for the 4th round of submitting your own geology memes. Okay. And there's already some good ones. So submit those. And later today, I will compile the winners from exam 1 on the memes that got the most votes. Okay, so let's go back to metamorphic rocks. And this is a little bit of a review from last day, but kind of helps us bridge the gap into the next spot. So what is going on in a rock during metamorphism? So as you change temperature and pressure, you're doing a couple of things. You're changing the mineralogy and the structure in those rocks, okay? The changes in mineralogy are going to occur based on what minerals are stable under certain temperatures. And this will differentiate into felsic, remember the quartz-rich minerals, and mafic minerals, the ones that are rich in magnesium and iron, okay? That differentiation kind of sorts the minerals out into bands. So gneiss, right? You've seen gneiss around here in New Hampshire and some places in Vermont, and it's got that sort of black and white zebra striping to it, right? That's the banding from the arrangement of quartz-rich, light-colored minerals and mafic, dark-colored minerals. So the other thing that can happen in metamorphism is folding. So, the other mechanism by which we can cause metamorphism is pressure. And so if you exert pressure on something and change the stress direction along rocks, and you heat it up high enough that rocks begin to deform like plastic, you can create these sort of brilliant folds inside of rocks, right? So initially, as you start shearing and stretching and compressing mineral grains, right, you're going to make them more elongate, and eventually they can fold over on each other. And at the outcrop scale or the landscape scale, we get big folds in the rocks, okay? The other side of this, right, is the chemical reactions, right? As you begin to increase pressure and temperature, certain minerals are going to become unstable and new minerals will form, and that causes a differentiation of minerals into bands, okay? So we can classify metamorphic rocks based on their grade. This is a measure of the intensity of metamorphism due to changes in temperature and pressure, okay? The way that we classify metamorphic grade is based on the types of rocks and minerals that we find inside of them, right? So if we take our most simple type of rock to start with, a shale, right? It has not been metamorphosed yet, right? But as it goes through slightly higher temperature and pressure, it's going to become slate. As you keep increasing temperature and pressure kind of equally, you go to schist and then gneiss, and then eventually you reach temperatures where you start to melt crystals in the rock into liquid, and that partially molten rock is called a migmatite. Okay, so you can remember liquid hot magma, right? So the way that we understand metamorphic grade is really based on the rock type, but again, we understand metamorphic rocks based on the minerals that are found. Certain minerals are only stable at certain pressure and temperature conditions, okay? So what do I mean by mineral stability? Well, if you change the conditions of pressure and temperature, the stability of that crystalline arrangement of atoms and that chemistry becomes unstable and it begins to react. And eventually, if you reach a new equilibrium set of pressure and temperature conditions, the minerals are going to adapt and into a form that's stable. Okay, this is in metamorphism called metastability. All right, so this is a little bit hard to visualize, right? Because it's going down deep on underneath the earth. So let's use another example. Okay, Humpty Dumpty sits on a wall, right? He may be able to sit there for a little bit, right? That's a metastable position. Okay, so he's not going anywhere. All right, but things change. All right, Humpty Dumpty takes a great fall, so he's no longer stable. Right, his reality is becoming very different until he reaches a new stable environment, right? So when he collides with the floor of the ground, right, and spills his yolk everywhere, right? Now he has changed, right? And he is now stable in his new environment. So we can think of metamorphic minerals and metamorphic rocks as being similar. If you leave conditions of pressure and temperature in one spot, the rocks and minerals are going to stay the same. But as you crank up the heat and pressure, you're going to change what minerals are present. Okay? So here's a little bit more complex explanation of metamorphic grade. Okay? So remember, we only get metamorphism at sufficiently high temperatures and pressure. And so our protoliths start below 250 degrees centigrade. As we move up in temperature, we go to low grade, 250 to 400 degrees C, to medium grade, 400 to 600 degrees C, and then our high grade metamorphic rocks between 600 and 850. Okay, so again, why is it limited to 850? Well, that is the temperature at which minerals begin to fully melt. So now you don't have a metamorphic solid state rock, you have a liquid, and therefore an igneous melt. Okay, so depending on what rock you start out with, and as you progress through these increasing metamorphic grades, you are going to produce different metamorphic minerals, right? So we've been talking about the more simple one, where we go from slate, which is essentially made out of clays, right? As shale, which is made out of clays, and as you metamorphose shale, it turns into a slate. And the first mineral that develops is one called chlorite. It's kind of a greasy green mineral. And as you keep on increasing the metamorphic grade, you begin to develop micas like muscovite and biotite. These are those sheety minerals you may have seen in Lab 6 if you were able to do that mineral lab. It's also what we used to make glitter out of. And then eventually you get to quartz and feldspar, and then garnet and storolite and kyanite. These are higher grade minerals. So if you find those minerals in the rock, it tells you about pretty intermediate metamorphic conditions. And then once you get up to really high temperatures and pressure, you end up with sillimanite, which is a polymorph of kyanite. Okay, but we could look at a basalt, right? A basalt is a extrusive silica pore igneous rock, right? And it is going to have have a slightly different have a slightly different progression from zeolite to chlorite to epidote to amphibole to garnet and pyroxene. Okay? So when we pick up a metamorphic rock and we see what minerals are present in it, it tells us about a geologic history, right? It first of all tells us about what it started out as and what changes in temperature and pressure it has gone through in the past, okay? So we can have several different metamorphic environments, right? In the last lecture, I talked about the physical mechanisms of metamorphism, right? Like at the molecular scale, what is going on. But let's look at a geologic scale. What processes and environments can cause metamorphism in the first place, okay? So there are a few, and this is what we'll spend the rest of the lecture discussing: contact metamorphism, burial, dynamic metamorphism, regional metamorphism, subduction, hydrothermal, and shock. And so really, the way that we should think about each metamorphic environment is in terms of pressure and temperature, all right? So is it hot and is it under pressure, all right? So thermal or contact metamorphism. This just means a protolith comes in contact with something very hot, right? So that could be a liquid molten chamber of magma, right? That magma is very hot, and the heat that is being radiated from that molten liquid body is basically burning all of the pre-existing rocks around it. This can cause a sequence in the metamorphic grade along and away from the pluton or magma chamber. And this typically will generate non-foliated metamorphic rocks if it's just like the eruption of a pluton and there's no compression involved. So we would get things like hornfels, quartzite, and marble. Right? So if you have a pluton that intrudes into a limestone, you're going to develop marble, right? And so it creates these in mountain environments like here in Vermont, as well as in Western Colorado in this place called Mule Marble, which is like the coolest place I've ever been. I was only like 10 years old, and you go into this giant pit, like cavern, where they have been mining out giant blocks of marble. And you can walk around and just like everything in this beautiful bright white. So it's pretty incredible. Anyway, so let's talk about the next one, right? Burial metamorphism is basically as rocks are buried under more sediment and more sedimentary rock cover, the pressure increases, right? And as you increase the depth into the crust that the rock is, you're also increasing its temperature due to the geothermal gradient. So this type of metamorphism occurs at about 8 to 15 kilometers below the surface. And this is an important sort of mechanism to understand because it tells us about how a sedimentary basin is evolving through time. So sedimentary basins, like we learned about in the sedimentary rock unit, right? As you create uplift, right, and push something up, the load of that rock is going to create a depression, a basin that fills in with sediment. So as that process proceeds and you make a deeper and deeper and deeper basin through time, you're going to cause burial metamorphism at the bottom of that basin. That's important for understanding like the boundary between sort of like a Goldilocks zone. If it's too cold for oil and gas to form in sedimentary rocks versus it's too hot and too high pressure and all of the organic material burns away, basically, okay? Then there's dynamic metamorphism. This is metamorphism that is caused by sudden movements at or near Earth's surface. Okay? So this can be from fault movements. So the fracturing and crushing as rocks are grinding past each other near Earth's surface. That creates crushed rock, basically. So there's actually very little change in pressure relative to what goes on deeper in the Earth, and there's no change in temperature. So this is one that is completely achieved by cohesion or compression and shear. So the type of rock that forms in these very shallow, relatively cold, low pressure metamorphic environments is called myelinite. It is a fine-grained rock because it's been crushed, right, by that movement. And the grains in them become elongated because you have rocks that are sliding past each other, and that creates shear along surfaces, and it makes these sort of like lens-shaped rocks. So an example of where you might find myelinite would be in a really active tectonic environment. So we can go back to New Zealand. Right? Don't worry, I'm not going to make you draw a river profile. But here is the Wairau River from Lab 9. And if we go slightly south of there, right, we pass over all of these mountains that are bounded by huge faults. And slip and movement along those faults produces a lot of earthquakes. And so a couple of years ago, down here near Kaikoura, New Zealand, there was a really big earthquake, and it caused surface rupture, meaning that you literally were thrusting up new ground above the earth around it. And so what you probably were producing along that failure plane, or where the slip along the fault is occurring, was myelinite, right? So myelinite you can remember as being the one from slipping, okay? So this is at a very local scale, right? I'm talking about rocks that are forming through grinding along an individual fault. But if we zoom out, we can have a what's called dynamothermal, or more simply just regional metamorphism. So this is what happens over large areas from like a tectonic collision. So mountain belts in general, right? When you have a tectonic collision, right, you are increasing the pressure over the area, right, as you are colliding a rock or a plate with another plate, okay? You're also causing melting at depth, and that increases temperature, so you can get metamorphism from that. And as you increase the accumulation of a mountain belt, right, the taller it gets, the more mass it has. That means the thickness is higher, and there's a greater burden on rocks underneath, so you get more burial metamorphism. And then you also have compression and shearing, right? So you get folds in the rock. So if we look at, time one, right, we have a continent at a passive margin right here, but on the other edge of the plate, there is a subduction zone, okay? And then initially there's, volcanism, and there's accumulation of sediment. As this plate and continental crust ends up colliding with that plate, you create regional metamorphism, a big mountain belt. So the common example for this in real life today is the Himalayas, right? You have the collision of India with the Eurasian plate, and that is creating a massive continent-continent collision zone and giant mountain belt. You can't really understand what's going on deep in the earth at the Himalayas for a couple of reasons. It's hard to get to a lot of the rock faces there that are up high that have been exposed because of the elevation, and it's generally inaccessible. And also, you haven't really removed enough of the rocks on top to see what's going on really deep. So another example we can use to understand what's going on deep in the crust during a mountain belt collision is go to old, ancient collisional belts. And we live, or you go to school at UVM, in the former location of a big continental collision. So as the supercontinent Pangaea came together initially, right, when it assembled, you had big continental collisions, and it formed the Appalachian Mountains. Those mountains were as tall, if not taller, than the Himalayas, right? But over the last few 100 million years, those mountains have eroded away, and that erosion has exposed the deep interior of that metamorphic mountain belt. So we can go to the Green Mountains and the White Mountains and Massachusetts, and you get to see the rocks that were forming in the very deep parts of the crust from that collision. Okay, so, right, we are looking at stuff down here, when we look at what happened in New England. So New England geology is quite complicated because we are looking at, hundreds of millions of years of geologic changes, and also often the most complex things that happen on Earth's surface, which is mountain building events. Okay, so we can look at this diagrammatically, right? Okay, so here's regional metamorphism, and you can get many different individual types of metamorphic processes going on, right? So you can have the dynamic metamorphism along faults and forming myelinite. You can have contact metamorphism where you get at hot enough temperatures to cause part melting, and that you can cause like hornfels and quartzite. But you can also completely melt or nearly melt the rock and create migmatite. But you also just have really intense pressure and temperature, and you can cause the typical progression from shale, slate, phyllite, schist, gneiss. Right? So again, here in New England, we in Vermont live in sort of like this environment that has been completely cut away, right? Think of these mountains as the Himalayas. These are 30,000 feet tall, and we have cut these off by tens of thousands of feet, and the isostatic unloading has exposed the really deep parts of the crust. All right, so that is what's going on land. Now let's talk about out in the ocean, okay? So hydrothermal metamorphism is basically where water, hydro, that is hot, thermal, causes chemical alterations of surrounding rocks. Okay, the most common place on Earth for this type of metamorphism is at mid-ocean ridges as well as submarine volcanoes. So the way that this works is that you basically have sort of a water circulation system going on here. You have really thin crust, right? We're at a mid-ocean ridge, and there is molten magma very close to the surface. Cold water from the ocean is seeping through bedrock through cracks, right? It's groundwater. And as it sinks, it comes in contact with very hot surrounding magma. And that heating causes the water to rise and pick up dissolved metals from the surrounding rocks. And then it wants to go to the destination of lowest pressure and lowest temperature, right? Things always flow along a gradient. And it erupts out at the seafloor as what we call deep sea vents, which are sometimes called black smokers. And these are really special parts of the Earth in general because they are found at mid-ocean ridges very deep and are incredibly rich in biodiversity. And you have to remember we're at such great depths that there is no sunlight making it through the thousands of meters of water above. So all of that biologic activity is occurring in the dark, meaning that those whole ecosystems are thriving off of chemicals and heat. This has been proposed as possibly where life started initially at all. But the other side of this is that these black smokers, right, are carrying lots of dissolved metals, and when they reach the cold, low-pressure environment of the ocean, they precipitate out and form mineral deposits. Okay. You also get dissolved metals that are coming out in a cloud from the vent, and they eventually fall down to the bottom of the seafloor. And then we get this sort of circulation cell of groundwater, of cold ocean water being pulsed into the ground and then ejected back up. So I wanted to show you guys what these look like in real life.
When were these vent stacks first found?
Well,
I don't know.
They've sure been known for 30 years.
I believe it was in the 70s.
Yeah.
Okay, so your commentary is not very insightful here, but This is a black smoker. This is the chemical precipitate. This is the dissolved mineral-rich fluids that are coming out of the vent and being jettisoned out into the deep ocean water around it. You can also see sort of the waviness, you know, on like a hot summer day when you look across a black parking lot, you can see sort of that fuzziness in the air right above the blacktop asphalt, right? You can see that same thermal wave, waviness coming around in the water, the distortion of light. So these places, you know, they're often crawling with really bizarre animals like tube worms, and also you can have strange types of coral, strange types of crabs and lobsters, and they are all thriving off of the emission of heat and chemicals out of these vents. So they're pretty special places. Now, because it is Earth Day, and I wouldn't be a good geology professor if I didn't talk about Earth Day as it relates to geology, something that is important for us to think about is seafloor mining. Okay, so these deep sea vents not only are incredible biodiversity hotspots, but they are precipitating out of, you know, hot fluids coming out of the earth, very mineral-rich fluids. Okay, things like gold and silver, copper, right? Very valuable materials. So this naturally leads humans, especially today, to want to go and mine this stuff, right? But mining on the seafloor is, number one, very risky, right? You know, you have to have a ship floating out in the middle of the ocean and dealing with storms. It's difficult. You are sending a drill stem or some sort of machine thousands of meters below the sea surface onto the ocean floor. So these two things, the risk and the difficulty, makes it extremely expensive to do this. Now, you have to consider that what is going to make it worth it for someone to do this, right? The price of the product that you are after. So in this case, gold. If the price of gold increases, it is going to become more profitable and therefore relatively less expensive to go and do this type of mining. So around the world, often near mid-ocean ridges, there are places that have been staked out by mining companies to do seafloor mining. Okay, these are rights. They are not necessarily active mining, right? This is just a declaration of the right to mine the minerals. So this will, you know, be a problem for deep ocean environments. So there's a few reasons, right? One, when you bring stuff up to the surface and you put it in a big boat, you risk spilling it. Okay, so the BP oil spill, every oil spill that we have had out in the ocean, we spill the oil out of the ship floating in the water, and then it destroys the environment. This is different. You would be spilling metals, but it would obviously not be a good thing for near surface life. Okay, there's sound impacts to whales and submarine life, right? Because you have this loud giant machine roaming around. And then the worst part of it is that you are literally going down on the bottom of the seafloor and grinding up and sucking up all this sediment and disturbing it. This completely disturbs the seafloor environment, which is actually quite calm in most conditions, and it would basically destroy an ecosystem that has been evolving for millions of years with minimal interruption. So this would be an extreme interference from humans. And I think that as we go through the future, which is not looking economically bright, unfortunately for all of us, that often coincides with a really big increase in the price of gold. And that increase in price of gold makes it relatively less expensive to go do gold mining. So from last year, gold prices have increased 34%. And this means that it is that much less expensive for someone to go out and do this type of mining. So, you know, this is a thing to consider environmentally is sort of the side effects of economic downturn can often lead to increased environmental degradation from things like gold mining. Anyway, I'll get off my soapbox. Okay, then we can have subduction zone metamorphism, and these are environments where you have incredibly high pressures, right? You have one tectonic plate going underneath another. So extremely high pressure, but not that high of temperature. So low temperature. You create a rock called blue schist, right? And that is classified by the inclusion of a mineral called amphibole. And these types of environments can only occur at ocean, continent, or even ocean-ocean collision zones where you have subduction. These types of rocks build up in the accretionary wedge, which is basically like the pile of rocks that forms above the trench. So kind of think of it as like when you are plowing snow and you've got that big, wedge of snow in front of your shovel or something, right? That's a wedge of sediment that is accreted. That is what's going on in blue schist formation, is you have extremely high pressures, relatively low temperatures. And then the last type of metamorphism is actually special because it is extraterrestrial. Okay, so shock metamorphism is when you have really extreme pressure and temperature from an asteroid or comet impact on Earth's surface. So in addition to metamorphism, right, these type of impacts cause extinction events. So that is one reason that they're sort of important to understand. But at the metamorphic level, it creates these sort of bizarre structures, and one of them is called a shock quartz or shocked quartz. And it's basically quartz crystals that have been exposed to extremely high pressure and temperature, and it leaves behind this weird sort of fracture pattern in the quartz. So you guys have heard about the extinction of the dinosaurs, right? Obviously, and the theory on which that extinction event is based is not only based on like the fossil disappearance of the dinosaurs, but it's based on the occurrence of shock quartz in Yucatan Peninsula, Mexico, kind of where Cozumel is today. And what's that other? What is that one called? I can't remember. Anyway, Yucatan, part of Peninsula, and there's a lot of shock quartz found in rock layers around this area before the impact, from the impact. Okay, so now we should think about how to link our metamorphic environments to plate tectonics, right? We've thought about how pressure and temperature influences the types of metamorphism that occurs, right? From no metamorphism to low to medium to high grade, right? So we should think about tectonically what could cause these changes in pressure and temperature and their variability, right? So for changes in temperature, right, I think the most obvious one is volcanism, right? So volcanism at mid-ocean ridges causes seafloor metamorphism, hydrothermal alteration. Where volcanoes actually form, they can cause contact metamorphism, right? Sort of baking stuff around it. If we have a large-scale tectonic event where you have one plate colliding with another, you get regional metamorphism. And movement along individual faults at that plate boundary will cause the dynamic metamorphism. And as you bury sediments and sedimentary rocks under more rock, there's higher pressure, and so you get metamorphism from burial, and that can be done at an active tectonic boundary. And then, yes, we have to consider that not everything that happens on this planet is just related to plate tectonics. I know that's kind of the theme of this class, but when we have extraterrestrial events happen, like a asteroid impact, that causes changes to the surface of the Earth. So that's it for today, and Friday we will start talking about earthquakes.